So, in Raman spectroscopy what we said is, what is important is polarizability, how polarizable your molecule is. What is the meaning of polarizability? Before you start telling me some story, I will write. This is the definition of polarizability. What is E? Electric field, fine. What is P? No. P is induced polarization, okay, induced polarization. Alpha is the polarizability, okay. So, everybody knows how to write it in this format, but there is more to it. The thing is, polarizability is a very tricky customer. Let us say you are polarizing the electron cloud, you apply an electric field in this direction. You will think that the cloud will get distorted in that direction, but then you are talking about a finite cloud, right? Yeah, it is a tensor. So, what will happen is that even though you apply the field in this direction, you are going to see distortions in this direction and this direction also. Think of a balloon, okay, take a balloon and press it. Stretching a balloon is a little difficult, that is why I am saying press it, but that should not come in the way of your imagination. Press a balloon, what happens? Does it only get distorted along this direction? No. It gets distorted along this direction and this direction also. That is exactly what happens here as well. So, that is why it is not necessary, you cannot just restrict it to one direction. You cannot expect that a field in x direction is going to cause polarization in x direction only. Field in x direction is going to cause polarization in x, y and z directions. So, you have to write it in this kind of a matrix form, Px, Py, Pz is equal to, alpha will come as a matrix here, Ex, Ey, Ez, right. So, what you write here is alpha xx, alpha xy, alpha xz. What is the meaning of alpha xx? It is a proportionality constant, right, for, or you can say polarizability for field applied, polarizability along x direction for a field applied in x direction. Alpha xy is the polarizability along x direction for a field applied in y direction. Alpha xz is the polarizability in x direction for field applied in z direction. So, I can fill in the remaining ones. For y, alpha yz, alpha zx, alpha zy, alpha zz. And the other thing is alpha yz equal to alpha zy. We are not going to prove it, but then you can take it axiomatically. Alpha yz equal to alpha zy, alpha xy equal to alpha yx. Is there anything else? Alpha zx equal to alpha xz. Okay. So, now like you wrote mu equal to mu x plus mu y, bad handwriting taking over, plus mu z, you took the components of the dipole moment along x, y, z vectors. Here you see the components of polarizability come along planes, isn't it? X x, x y, when you write something like that, two coordinates are specified, right, that is a plane. So, components of polarizability are along planes. So, you can think like this, polarizability, you can think of polarizability as a 3-dimensional object. So, if you read Banwell's spectroscopy book, for example, they talk about polarizability ellipsoids, right. So, think of maybe a watermelon, okay, watermelon is a good model for a polarizability ellipsoid. When you cut a watermelon, what kind of a section do you get? Watermelon, knife, cut like this, cut like this, cut like this, whatever. What is the section? What does the section look like? Unless you are very bad at cutting watermelons, you get a plane, you get planar section. That's what so, parabola, hyperbola, I am not interested in that. All I wanted was that we get a planar section, isn't it? That's all that I wanted. So that is the meaning of these components along planes. Huh? Unless for some reason you cut like this, that is a different issue. Okay. So planes are important here. So now if you want to talk about Raman activity, what is important? X, Y, Z are not important anymore. What is important are the quadratic quantities involving X and Y and Z. Alright. So once again let us do our zooming in, zooming out trick, but before that let us go back to the previous slide. We want to see whether A1 dash is Raman active or not, and while we are at it we also want to see whether these are Raman active or not. You can see A1 dash, does it have some quadratic power, z square, x square and all that? Cannot see? There is something in the second column that is good enough. Second column is quadratic power. Now do you see? Something is there, right? So it is going to be Raman active. What? I am in the wrong page? No? D3H. D3H, A1 dash, the upper one, not the lower one. What does it have? Does it not have x plus y square and then z square? So it is going to be Raman active, because it is in the same symmetry species as some component of polarizability. It is not IR active because it does not share a symmetry species with x or y or z, but it does share a symmetry species with some component of the polarizability, and that is why it has to be Raman active. What are the other normal modes of vibration that we already talked about? E dashed and A2 double dashed. They are Raman active, they are IR active. Are they also Raman active? Let us see. E dash, something is there. What about A2 double dash? No, right? So now let me complete the story. So this is Raman active or not? It is Raman active. I will write active only once. Henceforth I will write only Raman. Okay. Raman was a very active scientist anyway. You should read Raman's biography. There are a lot of things to learn. Raman worked as an accountant in AG Bengal, Accountant General Bengal, right. So before going to office and after coming back from office, he discovered Indian Association for Cultivation of Science. Very thankful for that, because eventually I also did my PhD from there. So he discovered that institute. It was a defunct institute at that point of time. So he would go and do his research just out of curiosity, nothing else, right. And then from there he would go to his office, come back directly from office to there, work till late night, go back home. Of course, needless to say, Mrs. Raman was a very understanding lady, otherwise it would have been impossible. Alright, this is Raman active. What about E dashed? Is E dash Raman active or not? Huh? This is so, this one see is IR active as well as Raman active. Moreover, the IR spectrum is going to be XY polarized. So now see, you can very easily identify which vibration we are talking about. Okay, nobody does that in regular usage of IR, but this is really the power of IR spectroscopy that we are learning today. And what about A2 double dashed? It is Z polarized, IR active, but Raman inactive. Okay, so now if you record the IR spectra at different polarizations, and if you record Raman spectra, compare them, you can actually identify which transition is due to which normal mode. Okay. So whatever we are saying now can be verified directly by experiments, right? Fine. Let us take one more example. Which other example did we take yesterday? Ammonia. Ammonia. But since we are nearing 6:30, I am not going to take an example of ammonia. I will take another example which you are supposed to have worked out last evening. Okay? Yes. And of course, there is a reason why I want to take N2F2. Tell me which point group this is. C2H or D2H? C2H? Sure. Where is C2? This is C2, cannot even see. Okay. This is C2, right. Horizontal plane of symmetry is very easy to see. What else is there? I is there, right, center of inversion, and that is exactly why I want to discuss this and not some other example. Something nice will come out here. And what other symmetry operation can be possible? E, of course. What else? E, C2, I, sigma H. Okay. And since we are doing it, let us go all the way for the benefits of the esteemed members of this class who were not present yesterday. We will work this out, even though some of you might have worked it out last night, we will work it out now. I will write the character table for you. First line I think everybody can write 1 1 1 1, and first column also everybody can write 1 1 1 1. Are you convinced it is 1 1 1 1? Huh? L1 square sum over I Li square is equal to 4, right. Okay. So, now I will put in the others 1 minus 1, 1 minus 1, then 1 1 minus 1 minus 1, 1 minus 1 minus 1 1, almost like your water, is not it? And we are going to do it in a tabular fashion like what we did yesterday. This is Rz x square y square z square xy, Rx and Ry belong here, Zx, Yz belong here, then Z belongs here, X and Y belong here. You need to tell me what are the Mulliken names. I do not have to write 1 here because D is enough. Okay. Whatever is symmetric with respect to inversion, you give it great respect and call it G. And whatever is antisymmetric, you just point a finger and say U. Okay, Gerede and Ungerede. Okay, right. This is the character table for you. Before we go any further, let us talk about this Rx, Ry, Rz. I promised to do this yesterday. Huh? Rx, Ry, Rz. How do I talk about Rx, Ry, Rz? So, the principal axis is always taken as a z axis, right? Huh? X, Y, Z. So, this is the z axis, this is x axis, right. So, Rx means what? This kind of rotation, rotation with respect to the x axis. You can draw it like a little curved arrow pointing this way. So, if this is plus Rx, what is minus Rx? This. Now, let us see if we can work out the characters for Rx. Of course, it is given in front of you, that is not an issue. What is the character for E for Rx? 1, of course. Now, if I apply C2, what do I have to do? I have to go this way, right. This is the C2 axis, this is how I was rotating my arm, okay. Now I am performing a C2 without changing the direction of rotating the arm, so keep a watch on me. This is how it is, right. So what do I have? In the original coordinate, this is what the motion is like. In the transformed coordinate, this is what the motion is like, right. This and this, aren't they minus of each other? When I come towards you, I come down, and here when I come towards you, I come up, the negative, alright. So what is the character of Rx then? Minus 1. What about I? What about I? Not I, that I. If you invert, what will happen? Will it change or will it remain the same? Let us say I am coming down like this, I will invert and come here, the direction will not change, it will still be like this. Just draw the small arrows and see, you will get it. What about sigma h? What about sigma h? Where is sigma h? Here, right. So coming down from here, what will be the deflection? Going up, that is minus 1. That is how you can work out the characters of Rx, Ry, Rz also. Okay, not difficult. And of course, I mean, in a public place, if you start, doing all these things with your arms, then people will think that you are either crazy or a professor, so or both. So you should learn to draw small curved arrows and do it from there. It is not difficult. Fine, let us come back to our actual problem. What do I need to do? First of all, I should write gamma xyz. Help me with that, gamma xyz. Gamma xyz is just the reducible representation which contains x as well as y as well as z. How will I get it? 2bu plus au, right. In fact, I will just write it here also, 2bu plus au. Okay, understand what I am saying? Because x is 1, y is also 1. Very good. To which symmetry species did x and y belong? That is already a 2-dimensional representation, isn't it? That is why. Very good question. This is a doubt that should come to your mind if you are alert. Got it? Got what I am saying? If x and y jointly make up the species for a 2-dimensional representation, then you do not have to add, it is already 2-dimensional. But here x and y both belong to some 1-dimensional species. So, that is why you have to add 2bu plus au. Now, what will that be? Tell me, help me. 3 minus 1 minus 3 1. Everybody agrees? Now, what is the number of atoms that remains unchanged? How many atoms are there? 4. What is the number of atoms that remains unchanged under each operation? E 4, C2 0, I 0, very easy. What is the next step? What do I do? N minus 1 gamma xyz, right? Or maybe you can just make it gamma rot. What is gamma rot? Ag plus 2bg. I hope you are not too busy to miss why it is 2bg. Huh? We know why it is 2bg. Tell me what it is then. 3. Give some pause, because if you say 3 minus 2, 3 minus 2, I tend to think it is 1 plus 1, 2. 3 minus 1, 3 minus 1, very good. Then what do I do after that? Now I work out gamma vibration. So Shubhangi, this is exactly what we did yesterday. Are you following what we are doing? Huh? What is gamma vibration? How will I find the characters? N minus 1 multiplied by the character of gamma xyz minus the character for gamma rod. So 3 multiplied by 3 is 9 minus 3 is 6. A quick check, how many normal modes of vibration should we have? 6, right? Okay, so then so far at least we are fine. Then n minus 1 is minus 1, minus 1 into minus 1 is plus 1, plus 1 minus minus 1, 2. Okay, here what is it? Minus 1 multiplied by minus 3 is plus 3, plus 3 minus 3 is 0. Then n minus 1 here is 3, 3 multiplied by the chi of xyz is what? 3, right, plus 1, that is 4. Are we all on the same page? Do you understand? Achal, Shubhangi, this is okay? You follow? Everybody okay? Sure? Avinash is? Okay. Now what do I do? I break it down into the constituent reducible representations by using that important relationship of ours. So I get gamma vib equal to what? Gamma vib equal to, what will it be? 3Ag plus AU plus 2BU. 3 plus 1 4 plus 2 6. Do we all know how I am getting this 3Ag plus this thing? Are you all okay? Now, what do I do next? I want to assign the internal motion, right? But even before that, what we can do is we can see which one is IR active, which one is IR inactive. Okay? For that we will need to consult the character table, right? Remember what it is, 3 AG, AU, BU. You are entitled to be forgetful when you are a professor, right? Character table is already there. So now you tell me which one is IR active? AU is IR active and it is Z polarized. What about BU? IR active and XY polarized. Is AG IR active? AG is not IR active, right? Is AG Raman active? So this is Raman active. So now let us complete our search. Is AU Raman active? Is BU Raman active? No. And this is a manifestation of a general principle called mutual exclusion principle. What is the meaning of mutual exclusion? It is somewhat like saying if you are absent for the class, then you are not present in the class. Being absent and being present are mutually exclusive. Okay? Whatever is IR active is not Raman active, whatever is Raman active is not IR active. When does mutual exclusion principle hold? It holds when you have a center of symmetry. And why? See, the point is this, X and Y and Z. Won't you agree with me when I say that X and Y and Z all have to be antisymmetric with respect to center of inversion, with antisymmetric with respect to inversion, right? Because you have plus on the top, you have minus at the bottom. So, you do whatever you want except for E, well no, not whatever you want. If you invert, then this is what happens, it becomes minus, this plus, minus, no matter whether it is x or y or z. Okay. It has to be U symmetry. Okay. Now, and that is what is involved in the transition moment integral for IR activity. What about Raman activity? What is involved? The quadratic terms x square, y square, xy and so on and so forth. So, now you have something like U cross U, right. U cross U is G, it is like minus 1 into minus 1 equal to plus 1, that kind of thing, right. That is why we have this very nice situation where you have mutual exclusion. If you have point of inversion, then the modes that are IR active are necessarily Raman inactive, modes that are Raman active are necessarily IR inactive, and this is a very good way of experimentally determining whether the molecule has a symmetry of has inversion symmetry or not, alright, mutual exclusion principle. So, to complete our discussion here, what we should do is we should talk about the internal motion. What are the parameters that I can use? I can use gamma NN, that is going to be very unique, right. That is a one dimensional representation, right, and what will be the characters? All 1, is that right? NN, right, I am only talking about the bond length, there is no plus, no minus. So, it is totally symmetric, okay, and that is definitely going to contribute to this AG vibration, NN stretch. What else is there? NF, gamma NF. Gamma NF, what is the dimensionality of the basis? Mehak, problem? Before that you understood up to here? What I am saying is now I want to ascribe the symmetry, I already know what is the symmetry of vibration. Now I want to see out of these vibrations that are there, 3 AG vibrations, 1 AU vibration, 2 BU vibrations, which vibration involves NN stretch, which vibration involves NF stretch, which vibration involves bend, okay, alright. So NN stretch, that means you have to use the NN bond as the basis. When you use NN bond as the basis, then it is totally symmetric, okay. Now NF, how many NF bonds are there? This is 1, that is 1. So what is the dimensionality of the basis? 2. What will be the character of E? Okay. What happens when you apply C2? The 2 bonds interchange, so 0, right. I will not bore you by repeating that thing again. Then what about I? 0. What about sigma H? 2. What else can I use? The angle gamma NNF. NNF is the angle, right. So what will be gamma NNF? How many angles are there? 2. So what will be the dimensionality? 2. This will be 2. So quick check, how many normal modes have we already accounted for? 1 and 2 3 and 2 5. How many are left? 1. What would that normal mode be? This is a molecule. Can this be a normal mode? Can this be a normal mode of vibration? This bond coming towards you, this bond coming towards me, it is not a normal mode of vibration. It is a normal mode of rotation. isn't it? That is rotation, but this is a normal mode of vibration, both coming towards you out of plane and then both coming towards me, that is minus phase, right, that is out of plane. Let us finish with this story, N and F. What will be the character for C2? 0. What will be the character for I? 0. What will be the character for sigma H? So, when you break this down, what do you get? Do you get AG plus BU? So, 1 AG plus BU for NF, 1 AG plus BU for NNF. Have we accounted for everything? What have we not accounted for yet? AU. Have we accounted for the 3 AGs? Yes. This gamma NN is AG. This is AG. This one you said is AG plus BU. This one is also AG plus BU. What is left? AU is left. Okay. Can you see that out of plane motion is AU? Look at the character of sigma H. Out of plane, where is sigma H? The plane of the molecule is sigma H, right? So, I am saying this is plus and this is minus, plus, minus. So, this is plus. If you perform sigma H now, what do you get? Do you not get this? Plus, minus, plus, sigma H is, I do not have, I wish I had a long nose now, this would have been the plane then, right, this is minus. So, are you convinced that it is AU, at least the character of sigma H is minus 1, so that is your AU. So, what we have done is for trans N2F2, we have done a complete analysis. Now, you should be able to handle the rest. Okay.